Welcome back to QHSE Talks, where we don't just learn safety rules, we understand the systems behind them and the science that turns prevention into reality. In today's episode, we are diving into Chapter 30, Materials Handling and Storage, a topic that many professionals underestimate because it feels routine, familiar, even ordinary. But behind every lifted box, moving pallet, or traveling forklift lies one of the most significant contributors to workplace injuries and one of the most critical domains for advanced safety application. This chapter is not just operational guidance, it represents a direct alignment with CSP Blueprint 11, particularly Domain 1, Advanced Application of Safety Principles. At its core, materials handling forces safety professionals to evaluate real-world interactions between humans, equipment, and energy. Topic 6 of Domain 1 focuses on evaluating materials handling methods and controls, which makes this chapter central to CSP-level thinking. We're talking about manual handling strategies like diagonal lifts, tripod lifts, and power lifting techniques, but also mechanical systems like forklifts, hoists, chains, and rigging, where concepts like load centers, dynamic stability, and the stability triangle determine whether an operation remains controlled or becomes catastrophic. But the alignment doesn't stop there. Domain 1, Topic 7, challenges us to evaluate tools and equipment used within operational environments. Chapter 30 addresses this through practical analysis of handling tools, pry bars, roller crowbars, and shovels, including calculation-based guidance that connects ergonomic science with real productivity limits. And when we examine Domain 1, Topic 3, evaluating common workplace hazards, the relevance becomes even clearer. Struck by incidents, falling loads, conveyor pinch points, and equipment interactions represent energy hazards that emerge when systems are poorly designed or misunderstood. At the same time, Chapter 30 bridges directly into Domain 6, occupational health and ergonomics, particularly ergonomics and human factor principles. Manual material handling remains one of the most common sources of fatigue, musculoskeletal disorders, and lower back injuries. That tells us something important. The human body is often the weakest link in the system, not because people lack strength, but because workflows are frequently designed without respecting biomechanical limits. This chapter challenges us to move beyond training alone and toward engineering solutions that reduce physical exposure. And that's why this episode matters. Materials handling is the hidden backbone of industry, the constant movement that keeps operations alive. Yet it is also where many safety systems quietly fail. Risk doesn't always look dramatic here. It builds slowly through repetition, poor positioning, unstable loads, or small design flaws that accumulate over time. Understanding these mechanisms is what separates compliance-level knowledge from true professional competence.
We are effectively examining the hidden backbone of industry. And we need to understand why that backbone so often ends up breaking the human backbone. So let's start with the most vulnerable piece of machinery in the warehouse, the human machine. Okay.
Section 1 of our dive focuses on manual material handling. Now, reading through the source material, the first thing that jumped out at me is what I'm calling the prime directive of materials handling.
I know what you're going to say.
It almost sounds like advice for how to be lazy, but I know it's actually a high-level safety strategy.
You are talking about the hierarchy of prevention.
Right.
The rule seems to be, the best lift is the one you simply do not make. It sounds simple, but it is actually the most difficult thing to implement because it fights against human nature. In the safety hierarchy of controls, elimination is always the most effective step.
Eliminating the hazard entirely.
Exactly. If I can design a workflow where a human being never has to touch the box, I have eliminated the risk of a back injury 100%. You cannot slip a disc lifting a box if a conveyor belt is moving it for you.
But we don't live in a fully automated world yet. I mean, not even close. Things still need to be moved by hand. True. But the text emphasizes that before you engage your muscles, you must engage your brain to bridge that gap. We call it engineering the hazard out. Before you bend over, you have to ask, can a forklift do this? Can a pallet jack do this? Can a dolly do this? And the answer is often yes, but.
But it is astonishing how often we see workers carrying heavy loads simply because the mechanical aid was all the way over there on the other side of the room.
Yeah, it's just easier in the moment to do it yourself.
They choose the path of least resistance in terms of time, but the path of maximum resistance for their spine. So step one is don't lift it if you don't have to. But let's say we're in a scenario where the machine isn't an option. The conveyor is down, the forklift can't fit, we have to move the box. Okay.
The text talks about a phase called evaluating the environment. This happens before you even touch the payload.
This is the check the path phase. And this is so critical. Most people focus entirely on the object.
Right, on the box itself. They look at the box and calculate, is this too heavy? Can I lift this 50 pounds? They forget to ask, can I walk with this 50 pounds? Right. You pick it up, and suddenly you realize there's a pallet on the floor in front of you, or a door you need to open, or someone left a zip tie on the ground.
And that is where the injury happens. Trying to open a door while holding a heavy load is a classic recipe for disaster.
I can picture that perfectly.
It shifts your center of gravity. It forces you to twist, which we will get to in a minute, and it creates a moment of instability. If you trip over a loose board while you are holding 100 pounds, the kinetic energy of that fall is significantly higher than if you just tripped walking empty-handed.
You're falling with an anchor attached to your chest.
That's a great way to put it. An anchor. So clear the runway. Now let's get into the actual mechanics of the lift. The basic lift. We've all seen the generic advice. Lift with your knees, not your back. The classic.
But Yates gets incredibly specific here. He calls it the diagonal lift. Why diagonal? What is the distinction there?
The diagonal refers to the foot positioning, and it is the detail that almost everyone gets wrong. Most people approach a box and stand with their feet parallel, shoulder width apart.
Yeah, like you're about to do a squat in the gym.
Exactly. Like they're about to do a squat. And that feels stable. It's a solid base.
Feels very stable.
It is stable for lifting straight up and down.
Yeah.
But the real world isn't a gym. In the real world, you usually have to move the object somewhere. You have to turn to place it on a table or a cart.
Yeah.
If your feet are planted parallel and you turn to the side, what happens mechanically?
You twist your torso, your feet stay put, and your upper body just cranks around.
Exactly. And twisting is the absolute enemy of the spine.
Why specifically twisting? I get that it feels bad, but what's happening inside?
We need to talk about the anatomy for a second. Your intervertebral discs act as shock absorbers. They're like little jelly donuts between your vertebrae.
Okay.
They handle compression, straight up and down pressure, quite well. That's their job. But when you twist, while they are compressed, while you're holding that heavy box, you are applying shear force. It is like grinding a mortar and pestle.
Oh, that's a bad visual.
It is. The disc structure isn't designed for that shear. That is how you tear the outer rings of the disc and get a herniation. The jelly pushes out.
So the diagonal lift prevents this. How?
Yes. You stagger your feet, one foot slightly forward, one slightly back. Not a huge lunge, just offset. This stance allows you to pivot your entire body as a unit. You don't torque the spine. You rotate the hips and the feet. You turn like a tank, not like a twist tie.
Turn like a tank. That is a great visualization. I'm going to remember that. And the text also mentions hugging the load.
Hugging is critical because of leverage. It's simple physics. Think of your shoulder joint as a fulcrum.
Okay.
If you hold a 10-pound weight with your arms fully extended out in front of you, the force on your lower back is massive. It's many, many times that 10 pounds because the lever arm is long. The moment that the torque is high.
Right.
If you pull that weight into your chest, you reduce the length of the lever arm to almost zero. The weight of the object hasn't changed, but the force required to hold it drops dramatically.
So it's not about being stronger, it's about being smarter with the physics.
Oh.
So keep it close, stagger the feet, and pivot. That covers the standard heavy box. But what really fascinated me in this chapter were the specialized techniques. These are specific programs for the body that I had never heard named before, like the half-kneeling technique. I love this one because it solves a very specific problem that we encounter constantly. Picking up something moderately heavy from a low level, like the floor, and bringing it up to waist height. Walk us through it, because when I hear kneeling, I think of taking a break, not doing work. It's definitely not a break. Here is the breakdown. You go down on one knee next to the object. literally one knee on the floor. You slide the object close to your body, hugging it again, and you actually rest it on your bent knee for a second. Okay, so you're down on the ground with the object, and you've got it stabilized on your thigh.
Right. Now, here is the magic. You plant the other foot, the one that is up, and you use that leg to drive the lift. You are essentially performing a lunge to stand up.
I see. So instead of leveraging the lower back to pull yourself up,
Which is what most people do from a squat.
you are using the quadriceps and the glutes, the big leg muscles.
Exactly. You are using the biggest, strongest engines in the human body to generate that vertical force. And because you are starting from a braced upright kneeling position, your spine stays neutral. It takes the lumbar region almost completely out of the equation.
It seems like it would take a few extra seconds compared to just bending over and grabbing it.
It does. And that is why people resist it. It feels slower. It feels less efficient.
But in terms of energy expenditure and safety, it is vastly superior.
No comparison. It's the difference between a safe lift and a potential injury.
Now let's talk about the opposite end of the spectrum, the overhead lift. The text seemed pretty wary of this one.
With good reason. Biomechanically, lifting heavy objects above shoulder height is a nightmare for the body.
Why is that?
To get full extension overhead, most people naturally arch their back hyperextension. This compresses the posterior part of the spinal discs, which is exactly where you don't want compression. It also puts incredible strain on the shoulder capsule.
Plus, if you lose your grip, gravity takes over instantly.
Right. If you drop a box at waist height, it hits your toes. Annoying, but probably not a major injury. If you drop a box overhead, it hits your skull or your neck vertebrae.
Yeah, no thanks. The text is clear. Ideally, you just do not do this. You use a platform, a ladder, or a step stool. You want to get your body up to the height of the shelf so you're placing the object forward, not pushing it up. But if you absolutely must, if there is no ladder and the boss is yelling.
If you must, the technique is about core engagement. You have to consciously tighten your abdominal muscles to prevent that back arch. Squeeze your core like you're about to be punched. And you keep the elbows in. But really, if you were doing this regularly, it is a failure of planning, not a failure of technique. Moving to the lighter side of things, I love the name of this next one, the golfer's lift. I immediately pictured someone on the 18th green pulling a ball out of the cup. That is exactly the motion. And this is designed for a problem of repetition. Let's say you drop a pen or a piece of paper or a small tool. It weighs 2 ounces. It's nothing. But bending over at the waist to pick it up hundreds of times a day causes cumulative trauma. Micro tears, inflammation. It adds up.
But nobody's going to do a full deep squat or a half kneel for a ballpoint pen. It feels ridiculous.
Exactly. It's inefficient.
Yeah.
So we use the golfer's lift. It relies on a cantilever action.
A cantilever.
Yeah, as your torso tilts forward to reach the ground, one leg swings backward into the air.
Like a teeter-totter.
Precisely. Your spine acts as the beam of the teeter-totter. Because the leg acts as a counterweight, your spine stays straight. It doesn't round like a turtle shell. You usually use your non-lifting hand to support your weight on a knee or a nearby table.
Ah, okay, so you're bracing yourself.
You're creating a 3-point base. It is elegant, it's fast, and it puts zero strain on the lower back.
I've actually started doing this at home when I drop my keys. My neighbors look at me funny like I'm practicing ballet in the driveway, but my back feels great.
Let them look. You are exhibiting perfect ergonomic form. Tell them you're protecting your discs.
There was one more technique mentioned, the straight leg lift. Now wait, I thought the #1 rule of lifting was never lift with straight legs.
It's a bit of a misnomer, and it requires some nuance. It is not lock your knees and bend at the waist. That's still a huge no-no.
Okay, so what is it?
This is for a specific scenario where you cannot bend your knees because of an obstruction.
Like getting groceries out of a deep trunk.
Exactly. The car bumper prevents you from squatting, or reaching into a deep wire bin in a warehouse. You physically cannot get your legs close to the object.
So how do we do that safely without blowing out a disc?
You keep a slight bend in the knees, do not lock them. Then you pivot at the hips, not the waist. The source material uses the phrase, sticking the buttocks out.
We are getting technical now.
It's important. By pushing the buttocks back, you maintain the lordotic curve, the natural inward curve of the lower back. You keep the back flat rather than rounding it. Then you use the hip hinge, the hamstrings and glutes to pull yourself back up.
So it's more like a deadlift motion in the gym.
A very similar mechanic, yes. It is not as strong as a squat lift, but it is a necessary adaptation when obstacles are in the way.
It is fascinating how we have these specific software programs for body movement, but manual labor isn't just about bare hands. We use tools. And section 2 of the text dives into the physics of hand tools.
Right. And here we are looking at leverage and mechanics. The text highlights a tool called the roller crowbar.
Which sounds like a wrestling move, but I gather it's for lifting.
It is a force multiplier. A standard pry bar gives you leverage to lift something, but once you pry it up, you were stuck holding it.
Right, you've just transferred the weight to your arms.
Exactly. A roller crowbar has a fulcrum with wheels built in. It allows a single worker to lift a massive piece of machinery, thousands of pounds, just an inch or two. Just enough to slide a forklift tine or a dolly underneath. It turns a superhuman effort into a manageable one using leverage.
And then we have pliers and tongs. The text makes a distinction here that I hadn't considered. It's not just about gripping, it's about distance.
Distance from the point of operation. That's the key phrase. If you're working with hot parts, or in a hammering zone, or near a press, you do not want your fingers anywhere near the danger.
So the tool is basically a buffer zone.
Tongs are essentially prosthetic fingers. They extend your reach. They sacrifice some dexterity. It's harder to manipulate things, but they buy you safety distance. If the press malfunctions, it crushes the tongs, not your hand.
Now, this is where the source material took a turn that I absolutely loved. We moved from anatomy to straight-up math.
Science of shoveling.
Yes, example 30.1. I never thought I'd see an equation for shoveling dirt, but here we are. It feels like we are trying to turn a laborer into a calculator.
It's not about turning the laborer into a calculator. It's about the safety professional doing the calculation to protect the laborer. This is where safety moves from guessing to engineering, from work hard to work smart.
So walk us through the scenario. We have an employee cleaning spillover from a conveyor belt.
Right. So the scenario is you have a shovel that holds 25 pounds of material. The worker has to lift it to a height of 38 inches. The question isn't, can they do it? Of course they can do it.
Right.
Anyone can lift 25 pounds.
The question is, how fast can they do it safely and sustainably?
And the text gives us a maximum safe load for a 15-minute period. Where does that number even come from?
It comes from extensive physiological fatigue studies. NIH, the National Institute for Occupational Safety and Health, does this kind of research. They measure oxygen consumption, heart rate, lactic acid buildup.
So it's based on hard science.
Very hard science. So for this specific lifting geometry, the height, the weight, the frequency, the source data says the maximum safe load is 1,650 pounds over 15 minutes.
1,650 pounds. That sounds like a lot, but that's the total aggregate weight.
Right. So we do the math. 1,650 pounds divided by 15 minutes gives us a limit of 110 pounds per minute.
Okay, 110 pounds a minute. That's the speed limit for the body in this task. Exactly. That is the sustainable pace. Now, we know the shovel holds 25 pounds per scoop. So we divide 110 pounds per minute by 25 pounds per scoop.
And the calculator says 4.4.
4.4 scoops per minute. That is the safe work rate.
I have to be honest here. 4.4 scoops a minute. That is one scoop every, 14 seconds?
About that, yeah.
That seems incredibly slow. If I were a supervisor standing on a dock watching someone shovel 4 scoops a minute, I'd be tempted to yell at them to hurry up.
And that instinct is exactly why people get hurt.
Really?
Absolutely. Our intuition about hard work is completely divorced from the physiological reality of sustainable work. We see 4.4 scoops and think lazy. The cardiovascular system and the spinal discs see 4.4 scoops and say sustainable.
So if I push that worker to do, say, 10 scoops a minute, pick up the pace.
Okay, let's do that math. At 10 scoops a minute, he is moving 250 pounds a minute. He is more than doubling the physiological limit.
So what happens to his body?
He will hit anaerobic fatigue rapidly. His heart rate will redline. His form will break down. He will stop bending his knees to save energy. He will start jerking the load with his back. And statistically, that is exactly when the injury happens.
Wow.
The math proves that you cannot simply hustle your way through physics. You can for a few minutes, but you'll pay a severe price.
It effectively proves that the hustle culture mindset can be an injury culture mindset if you ignore the math.
That is a perfect summary. Let's scale up. We've talked about hands and shovels. Now let's talk about mechanical assistance. Section 3, hoists and rigging. This is where we start lifting things no human could ever hope to lift. Chain hoists. These are devices where force is provided by a drum or wheel with ropes or chains. They are incredibly powerful, but they introduce a new set of failure points because we are dealing with stored energy.
A lot of stored energy. And the text gets very specific about inspections. What are we looking for when we inspect a hoist? We're not just kicking the tires.
No, we are looking for signs of stress, signs of impending failure. If it uses wire rope, we look for broken strands, kinks, or something called bird caging.
Bird caging. That is a vivid image. What does that look like?
It looks exactly like it sounds. The strands of the wire rope unravel and puff out, resembling old wire bird cage. It means the core of the rope has been compromised or shock-loaded.
So the whole structure of the rope is failing from the inside out.
Exactly. It's a critical failure sign. If you see bird caging, that hoist is done. You tag it out immediately, it's a ticking time bomb.
And for chains, metal seems pretty indestructible.
Metal is ductile. It stretches before it breaks. And that is a good thing because it gives us a warning. We look for elongation. We actually measure the links. If the links in the chain look like they're getting longer, or if they're narrowing in the middle, sometimes called necking, it means the metal is fatigued.
It's losing its strength.
It has lost its tensile strength and is ready to snap under load.
The text also mentioned reeving. I have to admit that's a new word for my vocabulary. What is reeving?
Reeving simply refers to the path the rope takes between the hoist and the load block. That system of pulleys. Think of it like lacing up a shoe.
Okay.
The critical safety point here is ensuring there are no twists. If the ropes are twisted in the reeving, it creates friction and stress points that the system wasn't designed for. It can cause the load to spin uncontrollably or the rope to jump off the sheave wheel.
So smooth lines, no bird cages, no stretched links. Got it. Now let's move to section 4. The text calls this the beast of the warehouse.
It is.
We're talking about powered industrial trucks, forklifts.
The forklift. It is the absolute workhorse of modern logistics. But referencing OSHA Standard 29 CFR 1910.178, it is also a weapon.
A weapon, that's a strong word.
Think about it. These machines are heavy, often weighing 2 or 3 times as much as a standard car. They move fast, and they carry massive loads. The margin for error is razor thin.
The thing that blew my mind in this section was the geometry. I always look at a forklift. It has 4 wheels, it looks like a car, it looks like a stable square. But the text says that is a dangerous illusion.
It is a fatal illusion. Most forklifts, even the 4-wheeled ones, operate on a 3-point suspension system.
A triangle.
The stability triangle. It's an imaginary triangle, but the physics are very real. The 3 points are the 2 front wheels and a pivot pin in the center of the rear axle.
A single pivot point in the back.
Yes. That rear axle pivot is what allows the forklift to turn so tightly, but it means the machine is balancing like a tricycle, not a car.
So essentially, you are driving a 9,000-pound tricycle.
Correct. And the rule of physics here is the center of gravity, or cog. The combined cog of the truck and the load must remain within that imaginary triangle drawn on the ground between the wheels.
If the cog shifts outside that line,
Over she goes.
it's that simple.
The truck tips. It's not a mystery, it's just physics.
And the dynamics of this center of gravity are constantly changing, aren't they? It's not static.
No, it's incredibly dynamic. It's a living thing. Think about an unloaded forklift. The heavy counterweight is in the back, so the cog is near the rear axle, the wide part of the triangle. It's stable.
Okay.
Makes sense. Now, you pick up a heavy pallet. The weight is now on the forks, way out in front. That shifts the combined cog of the truck and the load forward, towards the front axle.
Towards the tipping line.
Exactly. You're moving the center of gravity closer to the edge of the triangle just by picking something up.
And then you have vertical stability.
Right. Imagine that stability triangle as the flat base of a pyramid. As you raise the forks, the cog moves up. As the cog goes up, the pyramid gets taller and skinnier. It becomes much easier to push the cog outside the triangle base. That explains the rule. Always travel with the mast at the lowest level.
Yes.
Driving with a raised load is basically begging gravity to tip you over. You've created an unstable, top-heavy system.
And then you add movement. Dynamic stability.
Momentum. This is where it gets really dangerous. If you were driving forward and slam on the brakes, the momentum throws the cog forward. If you are holding a heavy load, that forward shift can tip the forklift onto its nose.
And turn.
If you turn a corner too fast, centrifugal force pushes the cog sideways towards the outside of the turn. If it crosses the line of the triangle, the forklift tips sideways.
The text mentions the moment. Can you break that down?
Yes, in physics terms. The moment is the product of the object's weight times the distance from the fulcrum. In a forklift, the front wheels are the fulcrum.
The tipping point.
The tipping point. The further out the load is, or the higher it is, the greater the moment, or tipping force. This is why you have to carry loads all the way back against the carriage, as close to the mast as possible.
Okay, so let's say the worst happens. You turn too fast. The cog leaves the triangle. The forklift starts to tip. This is the moment of truth. What do you do?
Critical. This is life or death. The instinct, the human survival instinct, is to jump. Your lizard brain screams, "Get away from the falling object."
It makes perfect sense. I see a giant metal thing falling. I want to not be in it.
It makes perfect sense, and it is the worst possible thing you can do.
The text says,
Do not jump. Absolutely do not jump.
why? It feels so wrong to stay inside a falling machine.
Because of the overhead guard, the safety cage.
Yeah.
If the forklift tips sideways and you try to jump out the side, you will not clear the machine fast enough.
You're not fast enough.
You're not. You will hit the ground, and a split second later, the overhead guard will crash down on top of you. We see horrific injuries where operators are crushed by their own safety cage because they tried to escape.
So what is the protocol? What are you trained to do?
The tip-over protocol. It is a 4-step drill that has to be muscle memory. First, stay in the seat. Don't leave the seat.
Okay.
Second, grip the steering wheel tight. This keeps your arms inside the cage so they don't get crushed. Third, brace your feet firmly on the floor or brake.
So you're anchoring yourself in.
You're becoming part of the machine. And fourth, this is the one you have to visualize. Lean away from the direction of the fall.
Lean away. So if it's tipping left, I lean right.
Exactly. You are trying to keep yourself secured in the seat. You ride it down. The roll cage will protect you from the impact with the ground. It is the safest place to be. But you have to fight every instinct in your body to do it. That is terrifying, but crucial to know. Staying inside the beast is safer than trying to escape it. Let's move on to the environment where these forklifts operate. Section 5. The danger zone loading docks. The loading dock is a fascinating interface. It's where a static building meets a movable vehicle, and that disconnect is where the danger lies. You have a solid concrete floor meeting a truck bed that is sitting on tires and suspension. It moves.
The classic problem is the truck driving away while the forklift is still inside, right?
That is the catastrophic scenario. The forklift just drives off into thin air. But there's also trailer creep.
Trailer crew.
Yeah. Every time the heavy forklift drives into the trailer, the momentum pushes the trailer slightly forward, inch by inch. After 10, 15, 20 trips, a gap opens up between the dock and the trailer.
And the forklift's front wheels fall into that gap.
And it gets pinned. It's a major cause of accidents.
The text discusses chocking versus dock locks. I've seen wheel chocks, those rubber wedges you kick under the tire. Are those enough? The source material is pretty clear. Wheel chocks alone have proven inadequate. They are an administrative control. They rely on human compliance. Someone has to remember to put them there.
Right. Drivers forget to put them in, they slip on ice, they get crushed. If the driver forgets, the safety system fails.
So the solution is the dock lock. An engineering control.
Engineering controls again. A dock lock is a mechanical hook that rises out of the dock face and latches onto the ICC bar, that metal bumper on the back of the semi-trailer. It physically binds the truck to the building.
So the truck can't move.
The truck cannot leave, even if the driver tries to pull away. The engine will stall before that hook breaks.
And this is tied into a communication system, right? The lights. The red light, green light system. It is an interlock. It removes human error. When the truck is secured by the lock, the light on the outside turns red. This tells the truck driver, stop, do not move, and the inside light turns green. This tells the forklift driver, the truck is locked, it is safe to enter, and when they are done.
The forklift driver or dock manager hits the release. The inside light turns red, meaning don't enter. The lock disengages and the outside light turns green, meaning you are free to go.
It removes the ambiguity. There's no yelling, no hand signals.
It is a logic gate that prevents the accident.
What about when the dock is empty? I've seen those big bay doors open in the summer to let a breeze in. That seems risky.
It is a huge fall hazard. A loading dock is usually 4 feet high. If a forklift backs off that edge because the driver isn't looking, it's catastrophic.
So what's the rule?
The text mandates that if a door is open and no truck is there, you need protection. And not just a piece of yellow caution tape.
Right. A piece of plastic tape isn't going to stop a 3-ton machine.
No. You need bollards, guardrails, or rated netting that can actually stop the mass of a forklift from driving off the edge. It has to be an engineered barrier. Let's slide over to Section 6. Conveyors. These seem benign, just belts moving boxes, but the text flags some specific nasty hazards. Conveyors are deceptive. They look continuous and smooth, but they are full of what we call nip points.
Nip points? That sounds unpleasant.
It is. It refers to the point where the belt wraps around the pulley, the tail pulley or the head pulley, or where the belt goes over a roller. It creates a wedge shape that is moving.
Like a V shape.
Exactly. It effectively acts like a mouth.
And it's a hungry mouth.
If a loose sleeve or long hair or a glove gets caught in that nip point, the conveyor doesn't stop. It doesn't know you're there. It just pulls the material in and it pulls the worker into the machinery with it.
That's horrifying.
It can cause degloving injuries or crushing fractures in seconds.
So guarding is the key here.
Yes. Referencing OSHA 1910.212 requirements. You must have physical guards over those pulleys and rollers. You have to make it impossible for a finger or a sleeve to reach the nip point.
The text also mentions static electricity with conveyors. Why is that a safety issue? I mean, getting shocked is annoying, but is it dangerous?
In an industrial setting, yes, it can be very dangerous. Conveyors are constantly generating friction as the belt moves over the rollers. That builds up a huge static charge.
And a spark is a spark.
Exactly. If you have a static discharge, a spark in an environment with dust, like from grain or wood or flammable vapors, or even just fine packaging materials, you have an explosion or fire hazard.
So how do you prevent that?
Grounding and bonding the conveyor system is essential engineering to bleed that charge away safely before it can build up to a dangerous level.
And I assume lockout to gout, LO2, is huge here.
Absolutely. It's non-negotiable. The classic injury happens when a box gets jammed. The worker instinctively reaches in to unjam it without turning the conveyor off.
Because it's faster.
Always because it's faster. The moment the jam is cleared, the stored energy in the belt releases, the belt lurches forward, and the hand is crushed or pulled in. You must de-energize and lock out the power source before servicing any jam. Finally, Section 7, storage and environmental safety. It's not just about moving things, it's about where we put them. Stacking. Gravity again, it's the theme of the whole chapter. If you stack it wrong, it falls. The text gives very specific rules for different materials because they behave differently.
Like bricks. That seems straightforward.
You'd think so. But bricks in masonry, you can't just stack them to the ceiling. There is a height limit, usually not over 7 feet for a loose stack. And there's a tapering requirement.
Tapering, what does that mean?
Like a pyramid. For every foot of height above 4 feet, you need to taper the stack back by 2 inches. This keeps the center of gravity low and stable and prevents the column from toppling over.
So it's not a straight wall of bricks. It leans inward.
It has to. It's an engineered stack.
And lumber.
Lumber needs to be on sill supports that keep it off the ground for stability and to prevent moisture damage, and importantly, free of nails. A stack of lumber with nails sticking out is a tetanus and laceration hazard, even if it doesn't fall.
One last environmental factor mentioned was carbon monoxide. We talked about forklifts earlier.
Yes. If you are running internal combustion, forklifts, propane, or diesel inside a warehouse, you are generating exhaust. You're running an engine indoors.
And in the winter, all the doors are closed to keep the heat in.
Exactly. In an enclosed space, CO can build up silently. It's odorless, colorless. It creates a toxic environment. You need scrubbers on the exhaust. You need good mechanical ventilation. And you need active monitoring alarms to protect the workers.
So bringing this all together, we started with a statistic, 32% of injuries. And we've walked through the human spine, the mechanics of a crowbar, the geometry of a forklift, and the engineering of a dock.
It really is a synthesis of disciplines. Chapter 30 isn't just a list of rules. It's a manual for navigating a physical world that is indifferent to human fragility. We use leverage, friction, and hydraulics to do amazing things, but every one of those forces has a cost if mismanaged.
So what here seems to be that materials handling isn't just grunt work, it's a high-stakes environment where physics is constantly testing you.
Exactly. The difference between a routine workday and that 32% injury statistic is understanding the science. It's knowing that the forklift is a triangle, not a square. It's knowing that your spine is a lever that can be broken. It's knowing that 4.4 scoops a minute is the limit, not a suggestion.
Here's a final thought to leave you with. We talked about the stability triangle in forklifts.
The idea that something looks stable like a square car but is actually balancing on 3 points. It made me think, how many other systems in our lives are like that? That's interesting.
We look at a project or team or schedule, and it looks solid, it looks square. But if we really analyze the pivot points, would we find a stability triangle? Or would we one sudden turn, one shifted center of gravity away from tipping over?
That is a fascinating way to look at it. Stability is often an illusion maintained by keeping things balanced within invisible limits.
Something to mull over the next time you pick up a box, using the diagonal lift, of course. Lift smart, stay safe, and thanks for listening to this deep dive.
Stay safe out there.